discuss kinetic energy. Kinetic energy is exciting. Moving objects can do work. We all know this. We have all seen the claw part of a hammer pull a nail out of a piece of wood. We've all seen the head part of a hammer hitting a nail and pushing the nail into wood. And we have all seen bowling balls knock over a bunch of pins. Now, we're going to get into conservation of momentum, but we know that the total energy exerted by the hammer has to equal the energy experienced by the nail, and the energy imparted by the bowling ball has to equal the energy of the pins. The total energy has, before any event, has to equal the total energy after. That's conservation of momentum. Now, any object that's moving is said to be kinetic. Kinetic means moving. And any object that's moving has kinetic energy. The formula for kinetic energy is 1/2 mv squared, where m is the mass of the object. And remember, we always measure mass in kilograms. And the velocity is the speed, and this is, we can call it velocity, we may call it speed, and we always measure this in meters per second. Now remember, all energy is measured in joules. Kinetic energy depends on mass and velocity only. Kinetic energy has to do with motion. Now, in this relationship, sometimes we want to compare what happens when we change mass or change velocity. Because kinetic energy is directly related to mass, remember that is right over the equal sign. If I double the mass, then I'm going to wind up doubling my kinetic energy. However, kinetic energy is directly proportional to the square of the velocity. So, if I double my velocity, I have to square that. And so my kinetic energy, my new kinetic energy, will be 4 times my old kinetic energy. Now, the work kinetic energy principle is very straightforward. It says the work done by any force is equal to the change in kinetic energy. So, this is only valid if work is the net work. Now, if we were to go back to the bowling ball with the pins, pardon my sad little diagram there, then we have to look at the total work done on any object. So the total work done on any given pin is going to be the change in kinetic energy of that pin. Now, remember, work and kinetic energy are related. If work is positive, alright, that means the velocity is increasing. Remember, we said that work is positive when it's speeding something up. So, kinetic energy, because it's 1/2 mv squared, as it speeds this object up, it makes the velocity larger, so the kinetic energy increases as well. While work is negative if it slows an object down. So if it slows it down, that means kinetic energy is 1/2, okay, not working, mv squared. If my velocity goes down, that means my kinetic energy goes down as well. Another way to look at it, if my speed is to the right and my force is increasing, if my force is to the right, it's going to increase kinetic energy. While if my speed is to the right and my force is to the left, that is going to wind up decreasing kinetic energy. let's look at the hammer and the nail. Alright. When the hammer hits the nail, it does work on the nail. It applies a force that makes the nail move. The hammer's had some sort of change in kinetic energy. Let's say it has some kinetic energy up here equals 1 half mv squared. Let's say when it hits, the kinetic energy is 0. Alright, the hammer has had a decrease in kinetic energy. Alright, and that change has got to equal the work done on the nail. So in order to look at this, we have to consider both the hammer and the nail as part of our system. It's very important to identify your system.